So good morning, everyone. We are recording now. So I just want to go over this intuitive idea that we were discussing yesterday, and then we will jump into the more complex version, which actually works. Okay, but this one will still give you some intuition about the problem, right? So we will look at the tight graph, which we used to call H earlier, right? And depending on the dual feasible solution, if it has a perfect matching, then we would have a perfect matching that satisfies condition 1, which is saying that all the edges of the perfect matching have to be tight edges. Okay, sorry. Oh, I don't know what to do. Can you call him? There's a problem here on the display. Sorry. Those who are on the call probably will not see the problem. Okay. Anyways, so I'll just talk and not write anything. Okay. So if there is a perfect matching, we will have one that satisfies the first condition. Otherwise, the graph H with the tight edges does not have a perfect matching. And because this is a non-bipartite graph, we will be applying Touch theorem, right? So by Touch theorem, we know that there is a touch set, and that set, okay, so the problem is resolved. So we will use that touch set to update our dual feasible solution, right? And in the bipartite case, we were looking at these red colored edges to update our dual feasible solution, right? So what do we do in the non-bipartite case? That is something I wanted you all to try. How should we choose the beta? Does anyone have any suggestions on how to choose the beta? So we already discussed that the plan is to increase the dual variables for the odd components. They could either be trivial odd components, single vertex components, or they could be non-trivial odd components, right? In which case we'll be updating the capital Y variables for those cuts. Um, So we want to add beta to those, and we want to subtract beta from the touch set vertices, the corresponding variables, right? And observe that we are adding more betas than we are subtracting. So overall, we are improving the dual feasible solution. The question is, how should we choose beta? Any thoughts? What are the kinds of edges I should be looking at? Or what are the red colored edges that exist in the graph G, because G has a perfect matching, we can assume, but they do not exist in the graph H, in the tight graph. What do those edges look like? Remember, there can't be a touch set in the original graph, right? So in the original graph, when we put those red colored edges back into the picture, the touch set should be destroyed because the original graph has a perfect matching. So how can we destroy the touch set? Okay, I'll give you a hint. Uh, Supposing there are no edges in the original graph that join two odd components, then what can you say about the original graph? Sorry, it doesn't? I think you're on the right track. You can complete your right, because this is still a touch set, right? So in the original graph, if there are no edges joining two odd components, of course in this graph you can't have edges joining two odd components because they are components by definition, right? But in the original graph G, you have to have some edges between two odd components in order to kill the touch set. Otherwise, this will continue to be a touch set in the original graph, contradicting that the original graph has a perfect matching, right? So there have to be some edges in the original graph that go like this. Of course, they don't exist in H because it is not a tight edge, and therefore this is a touch set in that graph, right? Because these edges are not there. But in the original graph, you must have these kinds of edges. Okay, so that is one type of edge. I will actually call it type 2 for reasons that will be clear soon. And there is also another type of edge that may exist in the original graph, but is not in this graph. It could be between an odd component and even component. Notice that there could also be edges between two even components, but I'm not going to care about them because in the even components, we are not going to make any dual changes. The even components are irrelevant to us. Okay, so those edges could also exist, but I'm going to call these type 1. So type 1 edges are going between an odd component and an even component. And type 2 edges, which must definitely exist, they are going to join two distinct odd components, right? So these must exist. At least one of these types of edges must exist. Otherwise, Z is a touch set in the graph G itself. Does everybody see this point? If you don't have such edges in the original graph G, then this will still be a touch set. Because even if you have type 1 edges, type 1 edges are joining odd components to even components. So the whole component will still be odd because you're adding one odd number with a bunch of even numbers, right? So you will still get a bunch of odd components. Okay. Actually, maybe that is not a true statement. Sorry, that is not a true statement. I would like to revise myself. I just realized that you can have this situation. You can have two odd components joining to two even components, and then you could have an edge like this. And now this is not an odd component anymore because you're adding two odd numbers with two even numbers. Okay, sorry. I revised my statement. At least type 1 or type 2 has to exist. All the edges cannot just be joining even components. Okay, so actually this is not a true statement. My bad. So the true statement in that case is that at least one of type 1 and type 2 edges exist in G. Otherwise, for sure, Z is a touch set in G. Yeah. Okay. Yeah. So when I was preparing, I incorrectly assumed that you will necessarily have type 2 edges, but that's not true. You might just have type 1 edges and no type 2 edges. Okay, so this is type 2 and this is type 1, right? All right. Are there any questions or concerns at this point? All right. So now I want to ask you, how do we use these type 1 and type 2 edges to define our beta? Because remember, in the bipartite case, we looked at the slack of all the red colored edges and we took the minimum slack, right? So now how should we do it? So we want to look at the slacks of type 1 and type 2, but do we just take the minimum of the slack or do we have to be slightly more careful in choosing our beta, right? So let us consider consider the slacks of the type 1 and type 2 edges. So what is happening in type 1? Type 1 is going from an odd component to an even component. We are adding beta on one side, and on the other side, in the even component, we are not making any changes. Right? We need to make sure that if there is any type 1 edge, the constraint, the dual constraint for that edge is not violated. What is the dual constraint? Look at this one here. Right? This is essentially the dual constraint with equality, but in the dual it's less than equal to, right? So it's yu plus yv plus sum of all the capital YDs for the cuts containing that edge has to be less than equal to the cost of the edge uv. Anyway, so basically it seems like Windows did not give us any choice really. Perhaps people had been postponing updates for a long time, and today it just decided that it's going to do what it wants to do. Anyway, so in the meanwhile, let's discuss how beta is calculated, right? So are there any thoughts on how beta is calculated, right? So we are looking at two types of edges. The type 1 edge is joining an odd component to an even component, right? And we are doing an increment of the dual variable on the odd component, right? We are adding beta to the corresponding dual variable, right? So supposing your edge is uv, and let's suppose u is in an odd component, which could be a single vertex itself, or it could be a bigger odd component, and v is the vertex in the even component, right? So and this is not a tight edge because this is not in the tight graph H, right? So we are going to add beta for the variable corresponding to vertex u, or to the component to which the vertex u belongs. So how much can we add? How big can beta be? Any thoughts? Yeah, bounded by the right. So the slack is non-zero, which we know it is non-zero, right? Supposing the slack is 3, then it is bounded by 3, right? If I increase it beyond 3, the constraint for that edge will be violated. So for the type 1 edges, I need to look at the slack of the edge. That will be an upper bound on how much I can increase beta. Do you agree? Right? What about type 2 edges? In the type 2 edges, look at, there is something different happening, right? We are increasing, so both the ends u and v belong to odd components, and we are increasing beta. We are increasing the dual variable by beta for both of those vertices or odd components, depending on trivial or non-trivial, right? So we are actually adding beta twice. So what should the bound be in this case? We are not just adding beta, we're adding 2 beta. It should be half of the slack. Exactly. So for the type 2 edges, we should be looking at the slack divided by 2, right? So what we will do is we will compute the minimum. We will compute a beta 1, which will be the minimum of the slack of all type 1 edges. And we will compute a beta 2, which will be the minimum of all slack over 2 of type 2 edges, right? So it will be half of the minimum slack of type 2 edges, right? And then we will take the minimum of beta 1 and beta 2, because that is the best we can hope to do. If we choose greater than any of these values in our set, then we will violate at least one edge, right? So we have to choose the minimum over all these type 1 and type 2 edges, where for type 1 you take the slack, and for type 2 you take the slack divided by 2. Yeah, everybody happy? Okay, good. All right, so that is how we compute beta. All right, and now that the computer has restarted, we will be soon resuming the actual notebook discussion. Okay, so I'll just quickly summarize what we discussed and write it down. So what we discuss is the following, that for type 1 edges, we will compute beta 1, which will be the minimum of the slack of all these edges. Because in the type 1 edges, we are adding beta to one vertex or the corresponding odd component, right? But we are not doing any changes on the even component. So the total increment is just beta, right? And so we need to take the minimum of the slack of all edges such that E is a type 1 edge. However, the type 2 edges are more interesting because we are actually adding beta to both the ends, right? So if the edge is UV, we are adding beta to the vertex U and vertex U variable or the corresponding odd component variables, right? And because we are adding 2 beta, we need to take the slack divided by 2, right? So let's say beta 2 is half of the minimum slack among all edges which are type 2. If there is no edge of type 2 or type 1, then the corresponding beta I will be infinity. Okay, because it just means that there are no edges, so you cannot violate any constraints. Okay, so if the set is empty, then the beta 1 or beta 2 will be infinity. We know that both sets cannot be empty, otherwise the Z will be a touch set in the graph G, right? So one of these is going to be a finite number. Okay, and finally, the beta will be the minimum of beta 1 and beta 2. Okay, so that is how we are going to choose beta in this case. All right, so if we have a touch set, we will get a finite beta. We will add this beta to all the odd component variables, right? And we will subtract beta from all the touch set variables. And we will improve the dual feasible solution. And we can keep doing this until the graph, the tight graph H, has a perfect matching, right? At some point, you will reach a situation where you have a perfect matching because you're constantly updating the dual feasible solution. And you cannot do this infinitely because the dual is going to be bounded. I think this is something you might have proved on your assignment. The dual is bounded because the graph has a perfect matching. So there is a minimum cost perfect matching, and that is an upper bound on the dual anyways. Right? So in a finite number of steps, you will reach a tight graph that has a perfect matching. What's the problem? If you choose an arbitrary perfect matching in this tight graph, it will only satisfy the first condition, being that all the edges in the perfect matching are tight edges. What about the second condition? Because you have also incremented the capital Y dual variables. And the condition 2 is saying that whenever a certain capital Y dual variable is positive, that perfect matching has to meet the cut in exactly one edge. How do we make sure that the perfect matching we choose satisfies this second condition? In the shortest path case also we ran into a similar problem. There we found a nice fix by using directed graphs. Unfortunately, we are not dealing with paths anymore. We are dealing with matchings. So there is no easy way to ensure this. So there is apparently a way which would do it in finite amount of time, but to cover that I will have to spend quite some time. And I basically had a conversation with one of my algorithmic expert friends who gave me a suggestion on how this could be done. But it uses a um, significant number of concepts that would have to be covered, and I don't think it's really worth the effort because it will spend 2-3 lectures doing that, right? So what we are going to do instead is we are going to look at a polynomial time algorithm, uh, which is going to be similar to the Hungarian algorithm, which works for bipartite graphs. But because these are non-bipartite graphs, we also have to do a bunch of blossom shrinking and also unshrinking. So we are going to use the blossom method to update the dual feasible solution and to make sure that not only the first condition holds, the second condition also holds, right? So if we just try the naive approach, then we run into issues, and fixing that is not easy. And even if you do it, you won't get a polytime algorithm. At best, it will be something that terminates in finite number of steps, or you will get some non-polynomial running time. Okay, but I think it's good to see that the naive approach fails, which is why we need to do something more complicated. Okay, so the real problem is condition 2. This is the big problem. Okay, and we need to fix it. So now let's discuss how we are going to fix it using the Hungarian method kind of ideas and Edmonds Blossom ideas. Are there any questions or concerns at this point before we move on to a fresh page? Okay, if not, let us proceed to a new page. And I want to do things using an example. And we won't finish this example today, not because of Windows, even otherwise you would not have finished it. So let me not blame Windows for that. But yeah, we might do even lesser than what I expected. Let's see. So let me take a specific graph, G, and it's just a big enough example to illustrate all the points, but it's not as big as what we did for Edmonds Blossom cardinality version. It's just going to be too messy if we do something that big and too time consuming. Okay, so consider this graph. Um, let me give labels V0, V1, V2, V3, V4, V5, 6, and 7. Okay, and the costs of the edges are as follows: 2, 3, 4, 4, 4, 5, 6, 6, 4, 8, and 9. All right. So we want to find a minimum cost perfect matching in this graph using Edmonds Blossom algorithm for the cost version, which we haven't seen yet. But we will just go through this example and formulate the algorithm on the way. Okay. So let's start with a dual feasible solution. We know this is quite easy. It's exactly what we did in the bipartite case. Take the minimum cost over all edges, divide it by 2, and give it to all the vertices. And put the capital Y bar to be equal to 0. So let me first do that. Capital Y bar is 0. And the minimum cost is 2. So I'm going to give a +1 to everybody. For the dual variables, for the dual feasible solution, I will put a plus or minus so that you can distinguish from the costs. And the costs in this example are all non-negative. In fact, they're all positive, but it doesn't have to be. The cost could also be negative. Right? Okay. So this is our initialization. Okay. As you expect, as we proceed in this algorithm, at some point we are going to do some blossom shrinking. Okay. So we won't always be working with this graph. We might be working with a derived graph G prime. Because we already have a G prime, we will have a tree T. I'm not going to call H as a tight graph. I'm just going to refer to the tight edges. Okay. So rather than using H as a tight graph, I will just say E tight. And when I say E tight, I mean all the vertices and the edges that are tight for the current graph, which could be G or it could be some G prime. Okay. So the current E tight, it's basically all the vertices, of course. And there is only one edge, which is this edge, whose cost is 2. Okay. All right. At each point in our algorithm, we are going to have a matching. I'm going to call it M prime because we could be working with a derived graph. And in fact, you can also think of G as being G prime right now. Eventually, the G prime might change, but G will remain always the original graph. Okay. And let us set M prime to be empty. I am making specific choices because I want to show you specific features of the algorithm, right? Sorry. Right now G prime and G are the same, but in the future G prime will refer to a derived graph. So I'm just telling you from now, right? Sometimes I will not label the vertices, but you can tell by my drawing which vertex is which, right? I will try to draw them in a similar fashion. Okay. All right. So my current matching is empty, and I also want to maintain an M alternating tree at every point in my algorithm, right? So I'm going to choose some root vertex. I'm going to choose this as my root vertex. So the current root is V2. Okay. And rather than keeping size of the matching in mind, I want to keep in mind the number of exposed vertices. So the number of M prime exposed vertices is right now all of them 8 because M prime is empty. Okay. And now let us start the algorithm. So what does the algorithm do? It's similar to the Hungarian algorithm. So our tree is right now just a single vertex, right? So maybe I'll make it even clearer. The T is just the root vertex, which is V2, and the empty set of edges. Okay. So, okay. So in this tree, at this point, we don't have anything interesting. So we are going to look at all the black vertices of the tree, which is just one vertex, the root, right? So the tree, you can think of it as U and W, right? So U is going to be the black vertices and W is going to be the white vertices. So maybe I'll just make this vertex black over here to indicate it. Okay. So at this point, the only thing I can do is look at the edges going from the black vertices of the tree to outside the tree. Sorry. Oh, it will go away soon. It should go soon. Let's wait. Yeah, there is some display problem, but it will be resolved soon, I hope. Yeah. Okay. Sorry. Okay, give me 1 second. I can't do anything here. I don't see it here. Yeah, I think they should fix this problem. Okay, good. All right, so the problem is resolved. Okay, so the tree is only one vertex, the black vertex, and the graph and the E-tight edges don't have any edges incident at the root vertex, right? So we can't grow the tree because the tree will always be a subgraph of the tight edges. Okay, that is the plan. We always want the tree to be a subgraph of the tight edge graph. Okay, so we can't grow the tree right now because there are no edges at the vertex V2, which are part of our tight graph, right? I may keep saying tight graph. What I mean is all the vertices with the E-tight edges. Okay, good. So what we are going to do is we are going to update the dual feasible solution in a systematic manner, similar to the ideas we just discussed before this using a touch set. Okay, so our touch set is going to be the white vertices of the tree, which is actually the empty set. And the odd components will be the black vertices of the tree where we'll be making the changes. Okay, so notice that the empty set is actually a touch set because if you delete nothing from this tight graph, you will get a bunch of odd components. Okay, So we are going to make changes only in the tree vertices or in the tree nodes, because later we will be working with derived graphs. Okay. So I'm going to add a beta to this root vertex variable, and I'm not going to subtract any betas because the tree has only one vertex right now. Okay, so all the dual updates will happen only in the tree. Okay, remember the tree has k plus 1 black nodes and k white nodes. So we'll be adding k plus 1 times beta and we'll be subtracting k times beta. Right. All right. So we want to choose the beta value, which we can add to this dual variable, which is plus 1 right now. Okay. So we look at all the edges joining the black vertex to other vertices outside the tree. Right. These are the two edges we look at. And notice that these are basically edges joining the odd component where we are making a change to vertices which are not being changed, right? The only change is going to be at this particular vertex. So we will just look at beta 1, which will be the slack of these two edges, and we will take the minimum of that. Okay. Anyways, as we proceed, things will become clearer. So right now, we will just look at the slack of two edges, which is v2, v0, and the slack of v2, v4, because our plan is to add beta to v2 and not make any changes anywhere else. Okay. So this is going to be 4 minus 1 minus 1, 2, and this is also 4 minus 1 minus 1, 2. So we can choose just this value because we don't have any beta 2 and beta 3 right now. Eventually we will have a beta 2, and also at some point we will need a beta 3. We won't get there today. Okay, so today we will be doing something simpler. So our beta is going to be 2. And I'm going to update this variable. Right, good point. Because we are only going to make changes in the tree, so we are only going to consider it as the slack of the edge, because we are not actually adding anything to the other end. So yeah, so it is technically an odd component. It is an edge of type 2, you are right. Okay, but we are not actually going to make any changes outside the tree. So the beta 1 and beta 2 actual definitions are going to change in this algorithm, but it's still going to be reminiscent of what we just discussed, right? Because we are making change only on one side, we'll take the slack. But when we make changes to both of them, both the ends, then we will take slack divided by 2. Okay, yeah. All right, so let's see, let me change so this plus 1, I'm going to change it to a plus 3. Okay, and this was done in step 1 of the algorithm. And I will also keep track of all the steps of the algorithm so that we know exactly how the things are changing, right? So the first step is a dual update, DFS update, right? The only change we have made is we have changed that plus 1 to plus 3. Okay. And all right. And now this also changes the tight graph, right? So the tight graph is now going to be, yeah, I think it's fine. Don't need to make all the changes. So let me change the beta. Let me remove this beta here. And the tight graph is now going to be, both of these edges will become tight. This edge and this edge. Okay. And right. And this is still the root. We are not going to change this. Okay. So our tree is still the same. It is a single vertex tree right now. And the matching has not changed either. So when we change the dual feasible solution, we are trying to make as few changes to other things as possible, right? We are not doing any other changes really. Okay. So now let's look at the tight graph and let's see if we can do anything interesting. So the root is still the vertex v2, and now we actually have an edge joining v2 and v4, which is a tight edge. So I can add this edge to my matching. Okay. Earlier the vertex v2 was isolated, so I could not find any augmenting path to increase the size of the matching. But now my tight graph has edges joining the root vertex to other vertices. So I can increase the matching. I can either choose the edge v2 v4 or I can choose the edge v0 v2. But I'm deliberately going to choose v2 v4. Okay. So step 2 is augment the matching M prime. We found an augmenting path which is single edge v2 v4, and our new matching M prime is just one edge v2 v4. Okay. All right. Remember, in the Hungarian algorithm, whenever we updated the matching, we basically restarted the whole tree, right? Every time we augmented the matching, we started with a single vertex tree by choosing some exposed node as the root. And if there is no exposed node, then we have a perfect matching and we are done, right? So now I'm going to choose some arbitrary exposed vertex as my root. Okay. And it's not completely arbitrary because I already made the choice earlier, right? So the new root is going to be this vertex. Okay. I'm trying to get to a particular situation so that I can show you something interesting. So let's call this the new root, r equal to v3. Okay. And let me remove the earlier root. And the tree is the same. It is again a single vertex tree with no edges. Okay. So what are all the changes happening here? We are resetting the tree to be r equal to v3, single vertex, and no edges. Okay. All right. Now again in the tight graph, if you look at the vertex r, which is v3, there are no edges incident at that vertex. So I cannot grow the tree inside the tight graph anymore. Right? Of course, I could have chosen a different route. That is a different story. But the route I have chosen, I cannot grow the tree within the tight graph anymore. So what I'm again going to do is I'm going to try to update the dual feasible solution. Right? So step 3 is again update the dual feasible solution. Okay. We are only going to add beta to the vertices in the tree, which is a single vertex root, and we are not going to subtract any betas. So once again, we are going to look at the slacks of the edges incident at this vertex. So let's look at the slacks. So the edges we are looking at are partial of V3, and these edges are V3, V1, V3, V4, and V3, V5. Okay, and let's look at the slacks. We might go up to 10 o'clock and I will try to stop at that point because we lost some time. Does anybody have a lecture after this? What time is your lecture?
NLP.
Okay. Sorry, anybody else?
Yes, sir, I too have NLP.
Okay. Then let me actually stop at this point itself. So let me complete the slack computation and then I'll finish the, yeah. So the slacks of these three edges are 3 minus 1 minus 1, 1, 4 minus 2, 2, and 6 minus 2, 4. Is that correct? Yeah. And the minimum is 1. So I'm going to increase the dual variable for this vertex. Okay. So let us add 1 to this guy, and this becomes a +2 now. And this was done in step 3. Okay. All right. And let's see how the tight graph evolves. So this edge v1 v3, its slack has now become 0, right? So this becomes a tight edge, and now this is our tight graph. Okay. Okay, and our matching, I want to remind you, it's a single edge. This is our matching. Okay. All right. So what I would like you all to do next is just complete steps 4, 5, and 6 on your own, and I will tell you the basics of that. So step 4, we are going to do, we are going to augment the matching because the root is this vertex v3, and we can extend it by including this edge. So this edge was included in step 2, and this edge will be included in step 4. Okay. So we are going to augment m prime once again. All right. And the new matching m prime, it's going to be 2 edges, v2, v4, and v1, v3. Okay. And at this point, I'm going to change the root, and the root is going to be made this vertex v0. Okay. And the new root is v0, and the new tree is single vertex and no edges. And now the tight graph has a bunch of edges. It has 4 edges in particular. So the next 2 steps you can do on your own. We will start at this vertex v0, and we will extend the tree because we will find these matched vertices, and we will add the vertices, and the whole tight graph will become your tree. Okay. So the next step is going to be extend the tree, and step 6, again extend the tree. And now the tree is going to look like this. This is your alternating tree, T prime. And at this point, something interesting is going to happen. Right. So up to step 6 is very standard stuff. At step 7, we are going to do something interesting, and I would like you all to try it yourself. Okay. So you have the tree, you have the matching with 2 edges, you have the dual feasible solution, which has not changed since step 3, right? So the dual feasible solution is what you see, and I want you all to try step 7 on your own and see what happens. Okay. Okay, so we'll continue this discussion on Monday. We will finish this example on Monday, and formalizing the entire algorithm Monday or Wednesday. I'm not too sure. And I believe next week, Thursday and Friday are holidays, so we will be resuming lectures after that. Okay. So see you next week, and please feel free to leave the meeting. Okay, so I'll stop recording and leave the meeting. Can't record the meeting.